Okay, so we are going to move on with section. Oops. So we're going to move on with section 2.5, or sorry, 3.2. And our example we're going to start looking at, it wants us to, this is example 5 from the book, and it wants us to compare, gives us a function f of x equals x cubed minus 12x squared plus 36x minus 16. And it wants us to compare that to that. And it wants us to compare the graphs. So this one is 3x squared minus 24x plus 36. So we're going to compare these two based on their graphs. So let me get Desmos and pull up the graphs of these so we can kind of take a look at that. And let's see. There we go. And so we want to look up, what is this? X to the third. X to the third minus 12x squared plus 36x minus 16. And then the second thing we want to graph is 3x squared minus 24x plus 36. Okay, so our graph looks like this. We're going to choose a slightly different window. We'll say negative to 10 is fine, but we want to look for the y-axis. We want to look at negative 20 to positive 20. Okay, and then let me just grab that graph and pull it on into what we can see. Okay, so in this graph, the red graph is our base function f of x. So this red is f of x, and the blue graph is the derivative, f prime of x. So it's asking us to compare, put this over here so we get some more space. It's asking us to compare between these two. So first thing we should notice, horizontal tangent lines on the base function. So horizontal tangent lines on the base function, those have slope 0. That corresponds to points where the derivative is 0. And that makes sense because a horizontal tangent line has slope 0, and the derivative is supposed to give you back the slope. So if the horizontal tangent line has slope 0, the derivative is 0 at those points. So we'll say f prime of x equals 0, where f of x has horizontal tangent lines. So that's the first thing we'll note. Second thing, if we look at all the points here where the horizontal tangent lines are positive, so if we look at points that have positive horizontal tangent lines on the red function, all those points correspond to positive y values on the blue function. So we'll say f prime of x is positive where f of x has tangent lines with positive slope. And then if we look through here where the tangent lines are negative, so we look through here, the tangent lines are all negative. That will, negative tangent lines correspond to parts where the blue graph is below the x-axis. So we can kind of write that up and say f prime of x is negative where f of x has tangent lines with negative slope. Okay, so that's kind of comparing and contrasting the graphs of these two things. Where the red function has horizontal tangent lines, the derivative is 0. Where the red function has tangent lines with positive slope, the derivative is above the x-axis. Where the red function, the base function, has negative slope of tangent lines, the derivative is below the x-axis. So we're going to move on over to getting two other definitions. So we're going to say we have this theorem about the derivative of e. So this is d dx of e to the x. That is just e to the x itself. So if you want to take the derivative of e to the x, you get e to the x back. The book also gives us this other theorem. And the book says, well, if you have d dx of b to the x, that equals m of b times b to the x. And the book isn't really clear as to what this is. It has us kind of investigate this and plug in some numbers. But I think in section 3.9, eventually they get around to telling you what that is. So instead of having this be kind of mysterious and then we learn about it later, we'll just, we will use that d dx of b to the x. We'll use the 3.9 equation. And it turns out it's natural log of b times b to the x. So if, for instance, I wanted to take what is d dx, the derivative of, say, 3 to the x, that would equal natural log of 3 times 3 to the x. So that's how you use it. So these are two theorems, derivative of e and derivative of exponential functions. So now we're going to go through and we're going to solve one problem asking us about tangent line stuff, and then we'll wrap the section up with a couple statements after that. So let's see here. Let's move on. And so we want to find, this is example 8. We skipped over a couple of examples. We want to find the tangent line. So find the equation of the tangent line to the graph of f of x equals 3e to the x minus 5x squared at x equals 2. So the x equals 2, that's going to be our a value for the equation of a tangent line. So we'll have y minus, it's f of a, but a is 2. It's this x equals 2 over here. So we'll have y minus f of 2 equals f prime of 2 times x minus 2. And so what we have to do is we have to figure out what is f of 2 and what is f prime of 2. What numbers go in there? So I'm going to do some scratch work kind of over to the side here to find f of 2 first. So f of 2, that will equal this equation here with 2 plugged in for the x's. So that will equal 3e to the 2 minus 5 times 2 squared. So that will be 3e squared minus, so yeah, it's 4 times 5 is 20. So f of 2 is 3e squared minus 20. Now we need to find f prime of 2. So to find f prime of 2, we're going to come down here a little bit and we'll do some scratch work and kind of calculate the derivative down here. F prime of x, this will be d dx of the derivative of the function. The function is 3e to the x minus 5x squared. So we say 3e to the x minus 5x squared. We're going to use the linearity of the derivative operator to break it across the subtraction, and we're going to push the constant out front. So the derivative of e to the x is just e to the x. It is its own derivative. That's by the theorem we just wrote down. We get minus 5 times the derivative of x squared. The 2 comes down. You get x to the 2 minus 1 is x to the first power. And then we'll say, all right, if we simplify that, that's 3e to the x minus 10x. So that's our derivative. We want to find what is f prime of 2 so we can plug it in here. So f prime of 2 would equal 3e to the 2 minus 10 times 2, which is 3e squared minus 20. So that is what we plug in for here. It happens to also be 3e squared minus 20. Normally these are different numbers. This just is kind of a weird case where that happened. And let's rewrite our equation of a tangent line. And that will be our answer to the problem. It's the equation of the tangent line. So I'm going to, since we got a lot of boxes and a lot of scratch work going on, I'll just use a different color so it's clear what our answer actually is. Okay, then we have one final thing that we need to look at. We got one last theorem. So this last theorem says this is differentiability implies continuity. And what the theorem says is if f is differentiable at x equals c, then f is continuous at x equals c. So if f is differentiable at x equals c, then f is continuous at x equals c. So for example, on this f of x here, we were able to calculate the derivative at f prime of x and evaluate it at 2. So since this function, we were able to take its derivative at 2, that implies that the function is continuous at 2. We're going to wrap up looking at one last example. So this is example 9. So we want to show that f of x equals absolute value of x is continuous but not differentiable at x equals 0. So we want to show it's continuous at x equals 0, but it's not differentiable. So to show it's continuous, we're going to look at the limit as x approaches 0 from the left of absolute value. So if you take absolute value of numbers like negative 0.0001, negative 0.000001, those become positive 0.001 and positive 0.00001. So the limit as you approach from the left still approaches 0. The limit as x approaches 0 from the right is also 0. So this tells me my two-sided limit as x approaches 0 of absolute value of x is 0. So the two-sided limit is 0. Since absolute value of 0 is 0, the function value is also 0. So these two are the same. So we get absolute value of x is continuous at x equals 0. So we have continuity. We want to show it's not differentiable. So to show it's not differentiable, we'll look at the limit of the difference quotient. So I'm going to say, what's the limit as h approaches 0 from the left of absolute value of 0 plus h minus absolute value of 0, all that over h. And what's the limit as h approaches 0 from the right of absolute value of 0 plus h minus absolute value of 0, all that over h. So we're going to use that with absolute value. Again, absolute value is kind of this V shape. The derivative is the slope of the tangent line. So when h approaches 0 from the left, we are approaching 0 from the left-hand side here. That's going to give us negative 1 back. When h approaches 0 from the right, we get positive 1 back. And so the left-hand limit and the right-hand limit are not the same of the difference quotient. So this says we are not differentiable at x equals 0. So we were continuous, but we were not differentiable. And the reason we're not differentiable is the difference quotient. It's sort of the slope of the tangent line, and the slope of the tangent line abruptly changes from negative 1 to positive 1 across the 0. So we'll stop there and